So now we're going to be moving on to Carey's text. And we're going to begin with an example of a t-test for two populations with equal variance. And the two populations consist of male and female falcons, and we're interested in their wing length. One of the things I really like about Carey is what he often does is he generates data and then he analyzes it. And that's useful because anytime we perform an analysis, we always make assumptions about the process that generated data. So by first generating and then analyzing the data, it strengthens that linkage between the analysis as a reflection of the underlying process that gave rise to the data. Now, before we go too far, what I want to do is step back and think about something we saw in week 3, and that's the distinction between a general linear model and a generalized linear model. And in most of our early statistical courses, we think of a general linear model as the observed values of y being equal to alpha plus bxi plus ei, where this is the dependent variable, this is the intercept, this is a slope, this is the independent variable, and this last thing is the residual. And we combine these two together, this is really a fixed quantity in the sense that it has no variability. All the variability resides with the residual. So for any given value of the independent variable x, you'll always get the same value for the dependent variable y. Another way to think about this bit here is that it's equal to mu I, the expected value of yi for any given value of xi. So we start off with the fixed component, and then we add on to it the residual. Where does the residual come from? Our residual is assumed to come from a normal distribution with a mean 0 and a standard deviation equal to sigma. That's the general linear model. The generalized linear model, once again, we're going to begin with mu I. So we're going to begin with mu I, but then we're not going to just tack on the residual. Rather, what we're going to assume is that we have a normal distribution which has mu I, this fixed thing, as its mean. But the variability comes in because this normal distribution is assumed to have a standard deviation of sigma. So both of these will ultimately give the same result. But as it turns out, what I'm going to use is this approach for, at least initially, for data generation. And we'll see this approach being used for the flowchart for this example of the t-test on the falcons. So, how we're going to generate the data. One way to think about the data generation is by using a matrix algebra approach. And that's what I'm going to do now. Now, if you're not familiar with matrix algebra or linear algebra, don't panic. Don't worry too much about what I'm doing. Just accept that the data is what it is. But for those of you who are familiar with matrix algebra, linear algebra, then I think the matrix approach is one of the clearest ways to visualize what's happening with the data. And so this is the formula that we're going to have. We can think of this as being the vector of the outcomes. This thing here we can think of sometimes as being the vector x, sometimes refer to that as the design matrix. This is B, or the coefficient matrix, and this is the matrix E, the residuals. I'm just going to set this aside for a moment and come back to it later. Let's look at some code. I'm going to begin by setting the seed equal to 567. Now, in this process, there's going to be a certain amount of stochasticity, a certain amount of variability. If I set a seed and then rerun the code at some later date with that same seed, I'll get the same results, notwithstanding the variability that's inherent in it. I'm going to begin by creating a couple of vectors. The first vector is going to be called sub, and it's going to be a numerical vector with 100 values from 1 to a 0 to 100 with length 100. So what that means is I'm going to have this vector sub that's going to be 1, 2, 3, 4, a whole bunch of numbers all the way to 100. And then the next thing we're going to do is create a character vector sex that's going to have C for concatenation, because it's going to have these two different components. The first component is the word male 60 times. The second component is the word female 40 times. So if I look at sex, it's going to be male, 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 dot, 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 female, female. Then I'm going to create dummy 1 and dummy 2. And again, concatenation, I'm going to combine two things, this and that. And this bit here is the number 1 60 times. So I've got, this is dummy 1. I'm going to have 60 followed by 40 zeros. And now thinking about dummy 2, again, it's going to combine two things. Now I'm just going to flip it around. So I've got 0 60 times and 1 40 times. So here's D2. It's going to be 0, 0, 0, 0, 60 of them, and then 1, 1, 1, 1, 1, 40 of those. And then I'm going to combine these two to create something called dummy. And if I'd been a little more clever, I probably would have called it design, because when I merge these two together, that is this thing here, that's the design matrix. And what we're going to see is that we're going to use this to get the value of the males, D1, and D2 is going to help us get the values of the females. We'll see how that works out later on. Here is our coefficient matrix, our B. There's our B. It's got two values. This is mean wing length for the males. And this one here is mean wing length for the females. And now I need to generate these E values. I need to generate these E values. And the first thing I'm going to do is create a vector called E that's just going to consist of 100 zeros. And these are essentially just placeholders. So get all those zeros. And then what I'm going to do is I'm going to have this loop that's open and close curly braces. And I'm going to loop through this 100 times. And we can think of this thing as having these implicit row numbers like that. So think about what happens. So I starts out at 1. So what happens when I is equal to 1? What happens when I is equal to 1? We've got the value of E at location 1 is going to be gotten from a normal distribution randomly. I'm going to extract 1, in other words, a single value from a normal distribution having these features. So what that means is, in that first iteration of the loop, that 0 is going to be replaced by whatever's given there. And then I loop through a second time. So I get E2. Again, it's going to be a single value drawn independently of the first value from a normal distribution having these features. So then the second 0 gets replaced by this, and so on and so forth, until ultimately, looping through 100 times, my vector E is going to have 100 independently drawn values from a normal distribution with these features. So now that I've got all the different components, I can put them all together using matrix algebra. So where the observed values are going to come from is going to be through this matrix algebra, and this is matrix multiplication. That's the symbol for matrix multiplication. So I'm going to take dummy and I'm going to multiply it by B. So there's dummy. That's my design matrix. And that's what it looks like. It's this pattern of ones and zeros. And I'm going to multiply it by B, where this is the mean for the males, and this is the mean for the females. So this is going to be a 100 by 2 matrix. This B is a 2 by 1 vector. And when I multiply these two together, if you think about the way, and you'll have to think about the way matrix algebra works, but what's it going to give me? What's it going to give me is mu I. It's going to give me a vector of the expected values of y for this experiment. Then what I'm going to need to do is I'm going to need to add the error term. So that gives me the expected value. That adds the error term. And now I'm essentially done. So I just make my data frame that has these 3 different components. It has subject, values that go from 1 to 100. It's got sex, the males and females. And it's got y that I've generated here. And there it goes. There are the data that I've generated.